the next application here is what is of interest to us here is an interferometer here. And so I assume here that so these are the XY axis. This is the Z axis. That I set here one aperture, yeah, and well, I don't specify, you know, the size. Thank you. I don't specify what is the shape of the aperture. It can be square, it can be circular, it can be anything, yeah. And I put another one, yeah, on the other side here. So it should be the same, of course, yeah. Like that. Yeah. Now I assume that the baseline between the two apertures, the center of the two apertures, yeah, is B. Now, if it was centered, yeah, in the middle, yeah. So let's assume that I would have centered the aperture in the middle, which is not the case. I would say, okay, I can represent the distribution of the complex amplitude, yeah, by means of the function A xy. Yeah? Now I should write here what, or I would call it A0 xy, A0 xy. Yeah? And now I would like to write here what is the distribution of complex amplitude, yeah, in the pupil plane, which is composed, yeah, of two apertures. So I say, okay, AXY is equal to A0. Now I say X plus B over 2 plus A0. And now here I say Y plus A0 X minus B over 2Y. Do you agree with that? Yeah. So I've just translated, yeah, one aperture on one side and the other one on the other side. Now I may write down that APQ, so the distribution of a complex amplitude in the focal plane, is equal to the Fourier transform, yeah, of the two. But the Fourier transform of the sum of two terms, yeah, is the sum of the two Fourier transform. Yeah, so it will be ft of A0 x plus b half y, which depends on PQ, plus Fourier transform of A0 x minus b over 2 y PQ. Yep. Now, if I'd like to calculate this, yeah, well, let's do it explicitly. Yeah, so it will be a double integration of A0 times x plus b1 half. Or you can make it explicitly, yeah, or you can use the translation properties that we have already established before, yeah. So how would you like to do? Explicitly? Maybe I make it explicitly this time, yeah. So I would say, okay, times exponentiation of minus I to pi of px plus qy dx dy. So I assume that I've forgotten, yeah, what is the translation property. Well, I will demonstrate it now. So I may define the variable w, which is equal to x plus b over 2, such that dw will be equal to dx, and this will become equal to, so I'm just developing this one, this quantity, A0 of w y times exponentiation of minus I to pi. So it will be pw plus qi dw dy multiplied by the exponentiation of what? It will be I2 pi times p times b over 2. Do you agree with that? This is additional term here which may get out of the integral. Now I would do the same for the other one, and then I would co-add them. Yeah? So what I would obtain at the end would be the following expression. I would find that it's equal to exponential of I2 pi. So the 2 disappears, so it will be I pi times BP plus exponentiation of minus I pi BP, like that, multiplied by what is left. And this is just the Fourier transform of A0 of xy, which depends on the variable PQ. Yes? So this is what is represented here, yeah? Now this may simplify as follows, yeah? So this will be 2 times the cosine of pi BP multiplied by the Fourier transform of A0 xy, which depends on PQ. And now I may calculate what is the intensity distribution in the focal plane, so which is APQ square. It will be equal to 4 times the cos square of pi PB multiplied by the Fourier transform of A0 xy of PQ square. And now you see what you can do, yeah? You can particularize this, yeah, to the case of a square aperture or to the case of a circular aperture, yeah? Now, in the first case, yeah, I think what we found was it was a at the power 4 of sine PPA over PPA square times sine of PQA on PQA square. Agree? Well, eventually, yeah, times A0 square, which was my I0, yeah. And now here what we found was A0 square multiplied by, I had a PR square at the power 2 times the module of the first order Bessel function, and it was 2 pi r times r prime divided by lambda, everything divided by 2 pi r prime divided by lambda. You agree? So I know everything. If I choose a square apertures, I have to multiply this by that. If I take a circular apertures, I have to multiply this by that. But you could still find the triangular apertures or banana-shaped apertures. Yeah? No problem. It's easy. What is very important, yeah, is this term. This is something new. Yeah. And well, the next picture, yeah, illustrate, yeah, exactly what you would obtain, yeah, if the 2 square apertures, so which have both the size of A, are separated, yeah, by a baseline D, which is equal to twice the value of their side. Yeah, so it's just an example. Yeah, so we see, wow, previously, yeah, for the square aperture, we were getting this function, yeah, and now we see that there is a modulation, yeah, and that it improves, yeah, the angular resolution, yeah, of the optical instrument, yeah. Now let's calculate once more, yeah, what is the separation between the two first minima, which will define, yeah, the angular resolution of the interferometer, yeah. So where we know that the cosine, yeah, will be equal to 0 whenever the argument will be equal to plus or minus pi over 2. Yeah? So this time it's pi over 2. And plus or minus, yeah, of course. It means that P times B will be equal to plus or minus 1/2, and that delta P times B will be therefore equal to 1. Delta P, yeah, I remind you that it is delta x prime over lambda f will be equal to 1 over B, which means that the angular resolution of the interferometer, phi, now will be equal to delta x prime over f, which is equal to lambda over B. Yeah. So we find that the angular resolution, yeah, of an interferometer, yeah, is inversely proportional now, not to the diameter of the aperture, yeah, but to the separation between the two apertures. Yeah. So if you set them very far away, yeah, well, you get a very good angular resolution. Of course, you only get one frequency. Yeah. Now, if you vary the separation, you get different frequencies, and well, you would have advantage also to change the orientation, yeah, and to cover the UV plane as well as you can. Yeah, what are the other 0? So for the square aperture, yeah, whenever the sign is equal to 0, you have a 0, yeah? This is this one, and this one. So this is a point-spread function corresponding to a single square, yeah? And now it's being modulated, yeah, by the the cosine square, and you get 0 here, and you get 0 here. So you improve the angular resolution, yeah, okay, along that direction. Now, along the Q direction, yeah, well, you see that there is no improvement at all, yeah? There is no improvement. The first 0 occurs here at the value of 1 over A. But D, yeah, is bigger than A because it's twice the value of A. So it only provides you an improvement in the angular resolution along the line, yeah, where you have the two single apertures, yeah. So what you say is that if you take a too long baseline and you observe a star, yeah, the visibility, yeah, was something like that. So, yeah, and then we found that for visible light, yeah, that this is a 0 visibility, so you don't see the fringes anymore. It would happen for 77 micron baseline, yeah, in the case of the sun, yeah. Okay, now, well, if you would observe, yeah, let's assume that I take the half that value, yeah, so 39 micron. So I have an interferometer, 39 micron. I observe the sun, I see the fringes, I measure the visibility, and I find that, wow, I have a point, yeah, sorry. This would be the visibility I would find, yeah, correct, yeah. Okay. So from one visibility and this one, I would try to fit the curve with just one point, yeah, assuming that it has such a shape, yeah, so a first order Bessel function, yeah. Okay, now this is true, yeah, if your assumption of a uniform disk, yeah, is valid. Now let's assume that you make measurement, and I will show you what I find. This is okay, and here I find this. So these are my measurements, yeah? And what I see is that I have a systematic departure, yeah? What could it be due to, yeah? So the scientists will say, well, probably it's not uniform, yeah? So probably it is affected, yeah, maybe by limb darkening effect, yeah? And so, well, let's consider now that I, zeta, eta is not a constant, but it has a, I don't know, polynomial dependence, yeah, on 1 or 2 parameters. Then I could adjust, yeah, those parameters and find that indeed I find a better fit now. And now I may derive, yeah, even the limb darkening law of a supergiant or whatsoever, yeah. So you see, more you have data points, better you may improve your model, yeah. If you have one data point and you assume one model, you from this, you will derive the diameter of the star, assuming that it is uniformly bright. But if your assumption is wrong, your angular diameter will be wrong. Yeah. So better have a few data measurements. Yeah. Tomorrow I will show you. Well, I skipped that transparency, but I give an example of a measurement, precise measurements which have been made on different stars. Yeah? And it is remarkable how, well, when you have only measurements, yeah, on the first maximum, well, the hypothesis of uniform disk is very good. Now, if you make measurements here, you see departure. So measurements, yeah, in the second lobe, yeah, provides you a lot of information on the limb darkening, but not here, not here. You need to go there to see second order effects. Yeah, yeah. What I would like to do, yeah, is to propose, yeah, to you, because you will have to do a small exercise, and to do the following. Yeah, it will be interesting, and it will address a question, yeah, that was raised by you, yeah, you yesterday. So let's assume, yeah, that so I represent here, yeah, the xy, x, yeah, no x, xy like that, yeah. Now I take here the center of one aperture, here's the center of second aperture. Now this will be minus b over 2. This will be b over 2. Now let's assume that here I put a rectangular shape aperture, something like that. So it's a rectangular shape aperture. Which size, yeah? Here is small a. This one is small b. And now here, so I'll try to do something similar. So here, what I do, yeah, I put another aperture, which is also rectangular, but the size here is a over 2. Yeah. So it is as if we were observing, yeah, with the two telescopes, which diameter are not the same. Yeah. Now, what is important to know, yeah, is whenever, yeah, there is a symmetry in your problem, yeah, where the response function, so the Fourier transform, yeah, will be a real expression, a real function, yeah. Now, this is not symmetric. So you will get complex representation, but since the intensity, yeah, is a square of the modulus of the distribution of the complex amplitude, it will be a real quantity, yeah. But you will have to play with complex numbers. And it will be very interesting, yeah, to see, in that case, yeah, what, and then you could take after, yeah, we will particularize to the case b equal 2 times a, and we will be able to compare, yeah, the response functions that you find with the response functions that we just calculated now. Another interesting problem that I may just address to you, especially to you there, yeah, because I'm thinking about adaptive optics, yeah. Well, I come back to the previous case here. I see that, well, I have a nice point-spread function, but there are secondary lobes, yeah. What should I do, yeah, at the surface of my single aperture, which is circular, yeah, to suppress these secondary lobes, yeah? So in principle, I'm quite sure, yeah, well, we assume that we have monochromatic light, yeah, But with adaptive optics, yeah, we could deform, certainly, the surface of the secondary mirror and make sure that the secondary lobes disappear. So we keep only the central lobe. So it will be a cleaner point spread function, yeah. So for those who do optical, yeah, astronomy, yeah, this is Airy disk is of course called the point spread function, yeah, due to the mirror shape. Convolution problem, yeah. Okay, so the convolution theorem states that the convolution of two functions f and j is given by the following expression. So I think you are familiar, yeah, with that, yeah? Yes or no? Yes, yes. And well, I just give here the examples, yeah? Two functions. So this is a door function, x over a. Here is another one, x over b. Now I want to convolve the two, yeah? So what you do, yeah? Well, you see that, yeah. So you define j for a value of t, then you take f, you reverse it, yeah, because there is minus t, yeah, and then you displace it, you multiply. So here is the result of the multiplication, yeah, it's just the intersection, yeah, of the two surfaces after translation of one with respect to the other. And then you monitor, yeah, as a function of x, yeah, the value you obtain. And so we know that here they are widely separated, yeah, so the multiplication of the two is 0, we are here. Then you will have a partial overlap, more, then total overlap, yeah. So this is during the time that this one will remain inside, and then, well, it goes away, so it declines again, yeah. So this is a convolution product, yeah. Now, yeah, here I'm just writing that every day when the sun is shining, it's possible to see nice illustrations, yeah, of the convolution product. So what you have to do, you have to look, yeah, at the projected images of the sun on the ground, yeah, and these are actually produced, yeah, by small holes, yeah, well, in the foliage of the trees, yeah. So this is an illustration, well, just taken here, I think, yeah, 2 years ago, you see, where you have the bamboo, and where you see on the sun, well, nice disk, yeah, and these are actually, yeah, well, image of the sun produced by a pinhole camera, where the hole, yeah, is among the leaves, yeah, of the tree. Now the problem is that you never have a perfect hole, yeah, where the hole can be extended or can be square or anything like that, yeah. And then what you can show, yeah. So just make the representation. So there is a tree here, and let's assume you have a small hole. Now I take it extremely small, yeah. So this is really a pinhole, yeah. Now you have the sun here. The rays go here through. They go here through. And so on the ground, what you see is not a circular disk, but you see an elliptical disk, yeah? Because the sun is not always at the zenith, yeah? When it is very high, then it's almost circular, like there, yeah? Now, if you take, yeah, well, the narrower diameter, and you measure it, yeah? So you find d centimeter, where typically it can be, well, 5 centimeter. Then if you multiply it by 114, so by 114, then here you find that it is 570 centimeter, so 5.7 meters. It means that the distance between here and the hole is 5.7 meters. Yeah? So this is a nice game, yeah, when you will see this circular disc, yeah, measure them. Then you put your head, yeah, the shadow of your head on the solar disk. Then you see the hole in the tree, and you know that the distance between the two, yeah, is the diameter, yeah, of the elliptical shape, yeah, sun multiplied by 114. Why by 114? Magic number. Now the answer is the following, yeah. If the sun is there, yeah, and you would like to hide the sun, yeah, take your thumb 1 centimeter in size, put it at a distance of 114 centimeter from your eye, and you may occult the sun, yeah? So 1 divided by 114 is the angular diameter of the sun in radian. So this is half a degree, 30 arc minutes, yeah? And therefore you find the same here because, well, the angle here is the same as the angle here, yeah? Yeah. Okay, now, so if the hole is really small, extremely small, this image will be faint, yeah, not very bright, but you will see many details, yeah. Well, if you have a lot of shadow, even here you could see some sunspots, yeah, on this image, if the sunspot is big enough, yeah. Now, if it's not the case, yeah, let's assume that, well, the hole in the tree is extended, yeah. What you will get here, yeah, is a blurred image, yeah. And what is in fact, yeah, the blurred image that you see, you could show that, well, the blurred image is equal to, well, the nice image, if the hole was small, so the nice image of the sun, convolve, so, well, I represent this as a convolution, yeah, multiplication, by what? Well, by the shape of the hole. By the shape of the hole. Okay? Now, if the shape of the hole, yeah, is extremely small, yeah, this is a direct function, and you find that the blurred image is equal to the nice image. Now, if you are too close to the hole, yeah, well, the nice image of the sun will be like a direct function, very small. And then you find that the blurred image is equal to the shape of the hole, yeah? And this is a nice experiment to make at home, yeah? So, well, we did that in our office, yeah? In Liège, yeah? Well, we just took a blackboard, yeah? A piece of cartoon, in fact, yeah? And here we made small holes, circular, here a little bigger, here still a little bit bigger. Then here, square hole, small, and a bit bigger, yeah. Then, well, here you could take a moon shape hole. Then you could still take a triangular shape hole. And you put it on the window, yeah? Then you let behind the sun, yeah, shining, yeah? Then what we do, yeah, we occult the window, yeah, with a black screen, yeah? So that in the room it's very dark, yeah? Then you take a sheet of paper, and when you bring it close to that, yeah? So of course what you see the shapes of the holes, yeah? Now if you go very far away here, you look, what you see on the screen, yeah? On all the screens, yeah, if you go very far away, is really the shape of the sun for all of them, yeah, So it doesn't depend on the shape, because, yeah, here the image of the sun is big compared to the size of the holes, so the hole behaves like a Dirac function. So you find that the blurred image, when you're far away, is always equal to the nice image. When you're close, well, you see the holes because the size of the sun is very small compared to the hole. So this is a Dirac function, so you find that the blurred image is the shape of the hole. And at intermediate distance, you see the product of convolution, yeah? So it's a nice illustration, yeah, how a product of convolution behaves, yeah, in 2 dimensions, yeah? It's very cheap, yeah, to do, yeah? And it's a lot of fun. So we have previously seen that for the case of a point-like source, having an intrinsic brightness distribution OPQ equal the Dirac function of P times the Dirac function of Q, there results the formation of an image in the focal plane, which is the impulse response. It's what we established here, yeah? So this is the impulse response for a square aperture, impulse response here for a circular aperture. Well, it's because we assume, yeah, that the star was located at very great distances, so it was point-like, yeah. And now, well, we saw that when we were, the response function is just the square of the modulus of the distribution of the complex amplitude in the focal plane. Yeah. Okay, now what we like to do is to consider the case of an extended source. Yeah. Well, this is not difficult because what we find is that if the real source, the intensity distribution. So this is a perfect, what you would see with a diameter infinity, yeah? A mirror which diameter is extremely large, yeah? This is the real source distribution. Now we know that the response function of our interferometer, yeah, is what? Well, just a moment, yeah, it's IPQ, yeah? So it is, this is in the case, yeah, we are looking at a distant star, yeah. Now, if you'd like to know, well, what is the brightness distribution in the focal plane, yeah, if the object is extended, well, of course, it's just the product convolution, yeah, of this one perfect image by the response function of your instrument, yeah. You make the parallel, yeah, with what I said about the solar disk and the pinhole camera. It's exactly the same scenario. So we find that the distribution of a surface brightness in the focal plane of an instrument is a real, yeah, where the ideal surface brightness convolved, yeah, with the response function of your interferometer. Yeah. Now, when we see that, yeah, we say, wow, it should be possible, yeah, to take the Fourier transform, yeah, of both sides. So let's do it. So if EPQ is equal to OPQ convolved with the response function of our interferometer, I take now the Fourier transform of both sides. So Fourier transform of this is equal to the Fourier transform of this. And now this I know that the Fourier transform of a convolution product is a point product of the two functions. So it's equal to the Fourier transform of OPQ multiplied by the Fourier transform of module of APQ square. You agree? Yeah. Okay. From this, I may infer that the Fourier transform of OPQ is equal to the Fourier transform of EPQ divided by the Fourier transform of the module of APQ square. Yeah. You agree with that? And now, well, I could say, okay, it means that OPQ is equal to the inverse Fourier transform of that, yeah? So it's okay, it's equal to the inverse Fourier transform of the Fourier transform of OPQ, which is equal to, well, to the inverse Fourier transform of all of that, yeah? So inverse Fourier transform of the Fourier transform of EPQ divided by the Fourier transform of the module of APQ square. Yeah. And well, if I look at those results, yeah, I have the impression that, oh, I may retrieve, yeah, the ideal object, yeah, by making the inverse Fourier transform of the Fourier transform of what I observe with my optical instrument. Yeah. So this is the observations. And this is the observation in principle of a point-like star. Yeah. Wow. Yeah, magic. Yeah. Does it work? Do you think it works or not? So this is called deconvolution, in fact. Yeah. It's a deconvolution. Now the reason why it does, well, it works to some extent, but not perfectly, because everything what I've written, yeah, would be true if I have all the spatial frequencies. But as we will see tomorrow, yeah, even when I observe a point-like star, yeah, I'm not getting information for all space frequencies. Yeah, there is always a limited range of space frequencies, and therefore, yeah, well, there is some limitation, yeah, to the interpretation of that result. Yeah, so it looks ideal, but in practice, it's not. It's known as the dirty map. That in fact, this quantity, you may get it from observations, but you may also get it, yeah, from the autocorrelation of the pupil function. Yeah, so we would get an analytical expression, yeah, for this, yeah, without observing a star. Yeah. Well, the advantage then is that it's not affected by noise. And when you make a deconvolution, yeah, noise is a big problem. Yeah. So at least we could get an analytical expression for this. We will see how tomorrow. Yeah. Otherwise, well, for optical observers, yeah, when you would like to know what is a point spread function, it depends on the atmosphere. So the only way to know is to look at a star, yeah, and get the point spread function from your observation. Then you cannot apply, yeah, the autocorrelation function of the pupil because you don't know what was the state of the atmosphere. But in the radio, yeah, well, you may infer this, yeah, from a well dirty map, yeah, and then proceed with a clean algorithm, yeah, to make the deconvolution, yeah, yeah, yeah. This is where radio astronomy is more powerful than well optical astronomy. That they are not so much affected by the state of the atmosphere. Yeah? Well, a little bit to some extent, but not as much. Yeah. But without atmosphere, you will not exist because you make your thesis on adaptive optics. Yeah. So you need the atmosphere, which is our enemy, but your friend.